All right, the beginning of each of these problems might be somewhat of a review. What we are going to do is look at these complex numbers. Remember that just means it could contain an imaginary number in there. And they're usually written in the form a plus bi. I have some formulas in the upper right. R is a distance formula, right? Squared a squared plus b squared. That's really nothing new. We've been using that already, especially when we are looking at a polar form. And then we are going to look as well as a new way of writing these complex numbers in polar form. Okay, so plot z. 2 plus 2i. So the real part we let represent a, which is similar to graphing x, so we just go over 2. And then the imaginary part is the coefficient in front of I, which is b, and it's also 2. So we're talking about this point. This point is 2 plus 2i. On the Cartesian coordinate system, yes, it is 2, 2. In a complex system here, it's 2 plus 2i. Evaluate the absolute value of z. Okay, the absolute value is what we are calling r here, right? It's a distance formula. Absolute value means distance, so the distance from 0, 0 to there, that's what we are evaluating. So absolute value of z, or absolute value of 2 plus 2i, is equivalent to the square root of 2 squared plus 2 squared, right, which is 8, right? 4 plus 4 is 8. And rationalizing it, or not rationalizing, I'm sorry, simplifying is 2 radical 2. So there was step 1, there was step 2. We get 2 radical 2. And last, to write this in polar form, I wrote this in the upper right, z equals r cosine theta plus I sine theta. That's polar form. We need theta, right? In the other, or previously in previous sections, what we did was found a polar coordinate, not a complex number, just changing a Cartesian coordinate to a polar coordinate. Now we're looking at complex to polar. A lot of it's still the same though. We need an angle and we need r. Okay, polar form, remember, was r theta of a coordinate. All right, so we still need r and we need theta, but now we write it in this form. The reason is, remember, x is cosine theta. Well, now we have a is cosine theta, right? And b is sine theta, but we have an imaginary, so I sine theta. An abbreviation, not all authors in text have this, but in this text we have z equals r cis theta. It just stands for the r cosine plus I sine theta. All right, so that's what the CIS stands for. Okay, so all we're missing is theta. Now that we have r, right, 2 root 2, which is also the absolute value of z, you have options. I'm used to solving this by doing tangent. Tangent theta is y over x, or in this case b over a, right, 2 over 2, which is 1. And you have to think, where's the tangent equivalent to 1? I mean, this one I could basically eyeball, right? It's 45 degrees, or pi over 4. But you could verify that, right? Use your charts and the unit circle, so theta is pi over 4. Now, like I said, you don't have to use tangent. You could use any of them. For instance, cosine theta, let's just do cosine, is x over r normally, right? Well, the x is the a in this case, so we have 2 over 2 root 2. And if we rationalize, we could reduce and rationalize multiply by root 2 over 2, root 2. Now we're thinking, where's cosine theta equal to root 2 over 2? Again, that leads to pi over 4, right? So use any of the information you have to get that angle. Sometimes you can even just see it. So for step 3, z is equivalent to r, to root 2, parenthesis cosine pi over 4 plus I sine pi over 4. That is your answer. Or you could write z equals 2 root 2 cis pi over 4. That is the polar form of that complex number 2 plus 2i. All right. So this point here, that's another way of writing it. All right, the next two are going to go quicker. One, because we just discussed how to do these. So some of the breakdown is easier, but also these are more trivial, I guess. Z equals 3i. All right, first we'll plot it. So we go up 3 on the imaginary axis. So there is the point 3i. Or if you really want an a plus bi, that's the same as saying z equals 0 plus 3i, right? I don't really see a need of putting 0, but you could. All right, there's it plotted. The absolute value is the distance. Well, I mean, I could count this distance, right? From here to here is 3. I could count vertically, so I don't really need to do the work, but you could. So first off, the absolute value of z I know is 3. Just to verify that, we would do square root of 0 squared plus 3 squared, right? Because 3i, which is square root of 9, which is 3. All right, theta. I don't really need to set up an equation here either, right? Theta, I know theta is pi over 2. It's a 90. That's the angle in which this point would lie on. So now I have r, because remember r is the absolute value of z. We're talking about the same thing. And we have theta. So we can finish this off by stating z is equivalent to 3 parenthesis cosine pi over 2 plus I sine pi over 2, or again z equals 3 cis pi over 2. All right, one more. Z equals -5. Now I don't have an imaginary part, right? I just go back 5. There we are. Again, we could write it -5 plus, oops, jumping ahead of myself, plus 0i. Okay, what is the absolute value? Again, we could count from here to here, right? It's 5. It's not -5. Absolute value is positive. We're talking about a distance. So z equals 5. And again, you could show it. It's the square root of -5 squared plus 0 squared, which is square root of 25, which is 5. All right, so r is 5. Now we need the angle. Well, this is 180 degrees, right? Or pi. So for 3, polar form is r, which is 5, cosine pi plus I sine pi. Notice that even though sine of pi is 0, I still write it in this form. This is polar form. Same thing with this one. I should have said cosine pi over 2 is 0. But in polar form, we typically still write it. Again, or z equals 5 cis pi.